Alrighty, that's time. If y'all wouldn't mind passing those up if you still got it. That was kind of standard point reactor kinetics equation terms and definitions. We've been talking about those equations for the last couple lectures. So, yeah, you could probably expect to see a question similar to that on exam two. So, if you missed any of those, make sure that you know those equations, that you know the terms in those equations, and that you know their units. Knowing those is kind of essential to understanding what the equations are trying to tell you about, and it makes them a little bit less mysterious. Today we're going to kind of continue with what we did with the point kinetics equations and with the n-hour equation. We're going to make sure we solidify our understanding of what those n-hour solutions are telling us about. And then we're going to use those solutions to start using that as a framework so that we can predict in a given reactor if a certain reactivity, insertion, or removal happens, how does that neutron population of that reactor evolve with time? So that's going to be like the main thing that we talk about today. And let's get into it. Um, I guess before we get into the actual content, I just wanted to remind us that midterm exam two is coming up. That's going to be in class on July 20th. So that would mean in a week plus one class, right? So, like, really almost 2 weeks from now is when we're going to have that exam. But I'm giving you the review materials now because this exam is going to be on the 20th, but I'm going to cover everything that's going to be on the exam after next class. So basically on the 13th, that's going to conclude the exam two material. I'm still going to lecture on the 15th, but it's going to be over the stuff that you'll see on the next exam. So like you should be here because that's going to show up on the final. But yeah, I wanted to give you guys the extra weekend plus a couple days to be able to prepare for that exam. So that's why instead of having it on the 15th, we're going to have it on the 20th. The format will be very similar to exam one. If you go on our Google Drive, you can find the exam materials that I posted. Um, there is a review and there is a formula sheet. So if you go to our drive and then you go to exam materials, you can see the guide, which is basically the review. It kind of just tells you what I just said in terms of what the scope of it is. Um, and it will give you some hints in terms of what kinds of derivations that you would want to make sure that you've practiced, because those might show up on the exam. So that exam guide is there for your benefit. Also, the exam two formula sheet is posted. The first page looks exactly like the exam one formula sheet. The second page is all of the new equations that we have talked about or will talk about for the second exam, and then the last page is the same as the exam one. So use this as you are studying, so that you kind of know based on what you had to do on the prop. Oh, question, Logan? Did you fix that typo on this one? Yeah, I did fix the typo. So now that equal sign is where it's supposed to be, and then all of these terms on the right-hand side of the equation have the appropriate signs. Um, so yeah, I did fix that. And yeah, use this to study, use this to kind of figure out if you do need to memorize anything that isn't explicitly given to you on the formula sheet, what you might need to memorize. And then, yeah, if you can, and similar story with exam one, where if you can do the in-class examples, the in-class derivations, the problem set questions, that's going to be like most of what you'll see. The derivation would be the only other thing, and those derivations are all listed in the review. So practicing those means that there won't really be any surprises. So like for our class, this is going to correspond to lecture 7 through 13, and it's going to correspond to like the end of chapter 4 that we didn't talk about on exam 1 up through chapter 7, and that corresponds to problem sets 4, 5, and 6. Speaking of which, I have problem set 6 You guys can pass those around. And yeah, those will be the last questions that you would want to be aware of and know how to do for exam two. So yeah, we've already kind of seen the structure of these exams, so hopefully we're recalling, making sure that if we can do those problem sets, it's going to be really important because a lot of the exam questions are going to be very similar to those. And per usual, so we did our first review session last yesterday. Hopefully we will, I mean, we'll keep doing those. Hopefully those are useful. And if you come, you get some added goodies. I made cookies last time. I think I'm gonna make banana bread next time. So you get some help on the problem set, you get some free food, and you collaborate with your colleagues. And have fun learning this stuff together. It's hard to learn this stuff, but if you do it with other people, that usually kind of uh, eases the burden a little bit. So just like a quick review of the stuff that we've been talking about over the last couple of lectures. We've been using the point reactor kinetics equations as like our main model to describe time dependence of nuclear reactors. Um, Knowing how to derive the point reactor kinetics would be a good thing to practice for exam two. Um, in this equation, N is the neutron density. But really, you can think of it as like an amplitude function in that, like we can take these equations and multiply through by given constants to convert that from an equation of neutron density to an equation of other things. Like if we were to multiply through by the neutron speed v, then we would have neutron density times neutron speed, which would be the scalar flux. If you multiplied through by the speed v and the fission cross section, sigma f, then you would have scalar flux times the fission cross section, which would be like a fission rate density. You could then take that and multiply through by E sub f, the energy per fission, and then that would be telling you about power density. So like you can convert these equations into other useful quantities to predict not just what the neutron density does, but what the power does, what the flux does. And ultimately, you just end up multiplying through by certain constants, which means that the shape of those functions doesn't change. It just kind of changes like the size of those functions, like what the values are on the y-axis. Um, when we talk about the point kinetics equations, they don't actually treat the reactor as a point. It really just means that we're assuming that that spatial flux doesn't change with time. And a lot of these quantities that appear in the uh, point reactor kinetics equations, like the reactivity rho, the delayed neutron fraction beta, a lot of these are end up depending on the neutron density, but in lots of problems we can treat them as constant, and that was what we started doing last time. Um, these are a system, a coupled system of I plus one ordinary differential equations. And that was kind of like what we were talking about last time with solutions to these equations. That last time we talked about looking at the homogeneous solution to those systems, where we're assuming that this total source term is zero. So that means that technically, when we were saying that the homogeneous solutions are a sum of I plus one exponentials. And so that means that like for the neutron density, you have a sum of this index ends up going up to I plus one. And because you start at zero, so zero is the first index, and then you have I more entries. So in total, you have I plus one terms of this sum. Each term has a different exponential time constant, the omega k's. And those omega k's are really important because they end up telling you about what my solution does as time progresses. If those omega k's are positive, then you could end up increasing exponentially with time. If they're all negative, then you end up decreasing exponentially with time. And if the time constant is zero, then you end up with a steady state solution as time moves forward. Um, and for the neutron density and for the precursor concentration, we have different multiplicative constants up front, but the time constants for each solution are the exact same. And if we want to find those time constants, we have to solve the n-hour equation. Um, this is also an important one to know how to derive. You could end up seeing that one on exam too. And basically, if you have I delayed neutron precursor groups, then there's going to be I plus one time, there's going to be I plus one exponentials that you're solving for, which means that there's I plus one time constants that we need to find. So there will, if you write this equation out, the n-hour equation, and solve it, you're going to have I plus one different solutions for those different omegas that will satisfy this equation. If you have more than two delayed neutron precursor groups, then it's very hard to solve this analytically, but it's very easy to use a graphing calculator or uh, like a MATLAB script or a Python script to do the root finding to figure out what values of omega satisfy the equation. Um, in general, remember that these solutions to the neutron density and to the precursor concentration are just a sum of exponentials. These time constants in the exponential have units of inverse time. And that's why kind of what the n-hour equation is like the inverse hour equation, because back in the good old days, these times were expressed in units of hours. And the sign of those omegas is going to be important, and it's going to tell you what your solution does as time moves forward. So this is the what this if you were to plot the right hand side of this n-hour equation, you're going to get these solid black lines that kind of look like weird like hyperbolic trig functions. And when you're plotting these, the independent variable is omega. So and what you do is you plot the right-hand side of this equation, which is the omega times big lambda, and then the sum of this guy right here. So that's what the right-hand side is, and the left-hand side is the reactivity insertion. So what you end up doing, like if your reactivity insertion is positive, that's what this top purple line is representing, some positive value of my reactivity insertion. And the roots of where this reactivity insertion intersects with the right-hand side gives me a bunch of intersection points, and the horizontal value of those intersection points falls on the omega axis. So the horizontal values of these points represents my different time constants. And so this is what those time constants end up being if I have a positive insertion, where one of those time constants has a positive value, and all of the other, in this case, there's I plus one of these omegas. So one of them is going to be positive if the insertion is positive. The other I of them will be negative. If the insertion is negative, which means that the reactivity insertion is like below the horizontal axis, then all of these time constants end up being negative. I of them are negative, and then even the omega zero one is negative. But the omega zero one is always the algebraically largest, and that just means it's the farthest to the right on like the omega axis. And if the reactivity insertion was zero, then all of these time constants, I of those time constants are going to be negative, and then the omega zero time constant is going to be zero. So there's some examples of plotting the n-hour equation and finding the roots on problem set 5. So that's an example that you can go through to practice solving these finding these roots for a bunch of different various reactivity insertions. And when you do that, you should see what we've been talking about here in terms of the pattern of what these constant time constants look like for various reactivity insertions. So this is kind of like the takeaway from that plot is that I of those omega k's are always going to be negative and real. And then the algebraically largest one, which we denote as omega zero, is always real and has the same sign as that reactivity insertion, right? When the insertion was positive, the value of this time constant was a positive omega value. When the reactivity insertion was negative, the value of this omega zero time constant was a negative omega value. And then if the reactivity insertion was zero, then that omega zero would be zero. And so if the insertion is negative, omega zero is kind of bounded between zero and that lambda one, which ends up being the uh, uh, minimum decay constant for group one precursors. So this omega zero is kind of bounded between zero and lambda one if the insertion was negative. And we talked about that minimum that group one with the smallest decay constant corresponds to bromine 87 that has a half-life of about 55 seconds, which means that that lambda minimum corresponds to about 1 over 80 inverse seconds. And that ends up being an important one to know, and we'll talk about that more in a sec. So then we said, okay, that reactivity insertion tells us if we are supercritical or subcritical or critical. So based on that reactivity insertion, we can characterize the criticality state of our system. And then based on what those exponential terms look like, we can characterize how does the population of my neutrons evolve with time. So if we were subcritical, then that insertion was negative, and then all of the time constants are negative. But if we were to say, how does this population look at some longer time t from the initiating event where we go subcritical, then it's going to end up being dominated by the term that has the algebraically largest time constant. And either way, though, that time constant was negative. So the like kind of later time behavior of my system is going to look like an exponentially decaying function. So if you're a subcritical system with no source, your neutron population will eventually decrease exponentially with time, following the behavior of that largest time constant. So when I was explaining this yesterday, I kind of felt like I was getting some weird looks. So I wanted to kind of plot what I was talking about. So so in this example, there's 5 delayed neutron precursor groups, which means we have I plus 1, which is 6 exponential terms. So these, the F0, F1, 2, 3, 4, and 5 are the individual exponential terms that would appear in my solution. And notice all of these are negative, but the omega zero term is the least negative in terms of its value for omega zero. It's the one that's closest, it's the one that's furthest to the right on a number line if we were to plot it. So notice the purple line, and it kind of, these time constants are becoming more negative as we go from F0 to F5. So notice F5 is the most negative term, and it goes to 0 very quickly. And then the terms that have slightly larger, slightly less negative time constants, they go to 0, but they kind of go to 0 a little bit slower. And if I were to, the S of X is just adding up all of these terms together. And so notice for longer time behavior, the red one is the exponential that terms to my, corresponds to my omega zero time constant. Notice that for later times, that sum and that omega zero term just like kind of fall right on top of each other. So when we're saying that the long-term behavior is a decreasing exponential based on the term with the algebraically largest time constant, that's just like a visual plot of what we were talking about there. So hopefully that kind of makes a little bit more sense if it was confusing at first. Um, so if the reactor is subcritical, sorry, supercritical, then one of those time constants is going to be positive and all of the other ones are going to be negative. So if we were to then ask the question, as time gets large, what is my solution going to look like? It's going to be dominated again by the one that has the algebraically largest time constant. And this one hopefully makes a little bit more sense because if one of my terms is a positive exponential and all of the other ones are negative exponentials, then as time goes forward, all of the negative exponentials are eventually going to decay away, and you're only going to be left with the positive exponential term. Therefore, if you're supercritical with no source, then eventually your population increases exponentially with time. And so this is a plot illustrating that, where it's the same setup. The only difference is that I've made this first time constant be positive. So notice again, all of the negative ones decay away. The most negative ones decay away the fastest, and the least negative ones take a little bit longer to decay away. But eventually, the behavior of my sum, which is the actual solution, is the sum of all of those exponentials, that long-term behavior just gets dominated by the term that has the algebraically largest time constant. And then we also talked about how it's the exact same idea. If the insertion is 0, then one of those time constants is 0, and all of the other ones are negative. So as time goes by, all of the negative ones decay away. The only one that you get left with is the omega 0 time constant, which e to the 0 is 1. So you basically just end up with a constant. So like if you were to think about this graph, if instead of this being e to the positive omega, if this was e to the 0, then what you would see is that you just have a horizontal line. If omega zero was zero, then and that's supposed to be a horizontal line, but I'm having a hard time drawing a straight line. And what you would end up seeing is that the sum would follow that dotted line. The dotted line of the sum would follow the omega zero solution. So yeah, so that's just to say if we have zero insertion and no source, then our population eventually is in steady state where it doesn't change with time. So basically what we're saying is that for longer time behavior, the solution is going to be dominated by the omega zero time constant. So like if I were to write my power, it's going to look like a initial power times e to the omega zero times t, where omega zero is the algebraically largest time constant. We can talk about the reciprocal of the time constant. The reciprocal of this time, if omega zero has units of inverse time, then what are the units of the reciprocal going to be? Just regular time, right? So we can just call this big T, and that big T is the reactor period. It's the reactor period, which, like Ravi just said, is going to end up having units of like seconds, or yeah, if omega zero is inverse seconds, then the period is just going to have units of seconds. So instead of writing our solution in terms of omega zero, we could write it in terms of the reactor period. And then we can kind of talk about a limiting case, which is if our that omega zero is kind of going to depend on the time constant, the decay constant for group one. And for a negative insertion, this time constant is going to be negative, and we're going to kind of be limited in terms of the reactor period by the minimum lambda. And we said that that minimum lambda was 1 over 80 inverse seconds. So therefore, the reactor period is kind of going to be limited by the reciprocal of that, which would be 80 seconds. So this is going to be equal to 80 seconds. And this is kind of an important number to keep in mind because basically what it ends up telling us is that if we have a negative insertion, the best that we can do in terms of dropping our neutron population is that in 80 seconds, the population would decrease by a factor of E. So if you were to like sketch a graph where you're showing an exponential decrease, you can actually use this fact to quantify to say, as that exponential decay is happening in 80 seconds of time, that population is going to drop by a factor of 1 over E. And if you look on this problem set 6, on the first question, it's asking you to sketch some different scenarios, and the answer to the first one ends up involving an exponential decrease, and that's where in the third part of that solution, you can actually quantify as that solution is decaying that decay over 80 seconds would happen and would result in the population decreasing by a factor of 1 over E. So that's just kind of like an example that you could take a look at where you would put that piece of information to use. Um, so this is kind of what we were just saying in terms of what our population is going to do if we have no source in the reactor. And these all correspond to the homogeneous solution to our problem. Um, and if you have like a differential equation that is homogeneous, then the solution to that is the homogeneous solution. But if you have that source term inside of the point reactor kinetics equations, then technically the solution for like N of t and Ci of t is going to be a homogeneous solution plus a particular solution. And for the neutron density, that particular solution for the neutron density of T, the particular solution looks like negative LP over rho times that total source term. So that becomes important when we start asking the question about how do these answers change if I have a fixed source? Well, that's what this S total is. This S total is some fixed source. Fixed source. So it's effectively a constant and tells me about like maybe in my reactor, I have like a Californium 252 source, which is used as like a neutron starter that just spontaneously emits neutrons into my reactor. So we can talk about, and in Dr. Adams' notes in chapter 7, he like works through the derivation, including this particular source, including this particular solution to talk about how the system evolves with time, or sorry, how the configuration of our system evolves with time if we have a fixed source present. So we can kind of talk about that now, knowing what the form of that particular solution is going to be. So if I guess I'm going to start from the bottom. If the reactivity insertion is 0, that means that we're critical. Then if we're critical before the source is added, it means that our production and our losses are balanced. And then if at that moment we were also to put a source in our system, that source is going to be spontaneously emitting neutrons at at a constant rate. So if we're emitting these extra neutrons at a constant rate, and we have a system that is able to perfectly multiply our neutron population so that from one generation to the next, the population is the same as it was before, then like if I started with 100 neutrons and then my source is constantly bumping in 10 neutrons per second, then when we get 110 neutrons in our reactor, our reactor itself can perfectly multiply those to give me 110 new neutrons. But then I have that source that's constantly adding 10 more every second. So once that source has added 10 more and we now have 120 neutrons, then our system can perfectly multiply those to give me 120 more. So it's like I started with 100 and I'm constantly adding 10 more per second, which are being multiplied by the criticality of my system. So as a result, we're going to end up seeing that the population increases linearly with time. Increases linearly. And it grows linearly kind of based on the source strength, we'll say, based on the value of that total source. So I think conceptually that one is pretty easy to understand. I also think that the supercritical one is pretty easy to understand because we know if we're supercritical, then one of our exponential time constants is positive and all of the other ones are negative. And if we're adding a source, then we have that homogeneous solution plus this particular solution, which is like a constant. So over a longer period of time, all of the negative exponentials decay away. So my solution really looks like a positive exponential plus a constant. And if you ask the question, if I have a function that's a positive exponential plus a constant, and I say, what is the overall behavior of that function? It's just going to be exponential, right? The exponential is kind of going to dominate that constant source term. So it's the same conclusion if I do have a source or if I don't. If the reactivity insertion is positive, my neutron population increases exponentially. So this will be increases exponentially. And then the last one is if my reactivity insertion is negative. And so we already said before that if my insertion is negative, all of my time constants are negative. So as time goes forward, all of those time constants being negative means that that homogeneous part of my solution just decays away to 0. And if that homogeneous part decays away to 0, all that's left is this particular solution. And this particular solution is just 3 constants multiplied together. So that means that if I have a negative reactivity insertion, then the end behavior of my system with a source present means that it basically just is a constant. The population is eventually going to reach a steady state. So that's what we can say here, eventually reaches a steady state. And that's kind of funny in the sense that if you remember, I think it was problem set 1 where we did an infinite homogeneous medium, and then we assumed that there was also a neutron source term. If you did that problem, this is actually the exact same conclusion that you should have came up with in terms of how does the system respond to the reactor being supercritical or subcritical or critical. And so it's kind of funny that with this very detailed treatment that we've done in terms of the time dependence and accounting for delayed neutrons, that the overall behavior of our system is exactly what we saw when we studied that like a more simple example of one group, one speed neutrons in an infinite medium with an extra source. So you might then be mad at me and you might be wondering, why do we have to go through all that work if we just got the same answer that we got with a more simple problem? And that might make you also think that delayed neutrons aren't important, but that's not the case. And they're important because of the fact that those delayed neutrons add negative exponentials into our solution, and those negative exponentials end up affecting the system response. And effectively, they end up making our reactors easier to control. So this is like kind of an example that I wanted us to take a look at to understand that this is my n-hour equation, but if there's no delayed neutrons, then that effectively means that my beta I values are 0. So if there's no delayed neutrons, then this entire term just goes away. And that means that my reactivity insertion just looks like omega times big lambda. And big lambda has it by definition, big lambda is just the prompt neutron lifetime LP divided by the reactivity K. Sorry, by the multiplication factor K. So that's kind of rewriting big lambda. But also, we can write the reactivity insertion in terms of K as well. How, how do how do we write the reactivity in terms of K? Perfect. Yeah, so that's going to be equal to K minus 1 over K. And so then what's going to end up happening is that these two Ks down here are like kind of going to cancel each other out. And so if I get omega by itself, that means that omega is going to be K minus 1 over LP. So if there's no delayed neutrons in my system, then I just have one time constant as the solution to the n-hour equation, and it looks like K minus 1 over LP. So if we know what that solution is, then we can plug that into our particular solution, and then we can kind of investigate using numbers how my population would respond as a function of time. So in a typical reactor, that prompt neutron lifetime is about this many seconds, 0.0001 seconds. So imagine that we had a reactor that was just barely supercritical, that it had a multiplication factor of 1.001. And then we want to ask the question, how much would the neutron population change over 1 second of time? And therefore, how much would the power change as well? Because if the neutron population changes by like a factor of 10, it means that the power is also changing by a factor of 10. And so the total neutron density, we can just write that as the initial density at time 0 times e to the omega t. And if that is like our function of time, and we're saying n0 is the initial amount, then we can plug in omega and we can evaluate this at t equals 1 seconds. So I'm going to have n naught times e to the omega t. And we already said that omega from the previous slide was K minus 1 over LP. So if I have K minus 1, then I have 1.001 minus 1. So in the numerator here, I have 0, 0, 1. And then it's divided by LP. So it's divided by this number, 0. I have a 0 right there, 0.0001. And that has units of seconds because it's the lifetime, prompt neutron lifetime. And I'm evaluating it at t equals 1 second. So in for the t, I plug in 1 second. And as we would hopefully see, my seconds cancel because I can't have units inside of my exponential. And if you were to work out what e to this quantity is, you're going to end up with 10. It's going to look like e to the 10. And if you were to then go to your calculator and plug in e to the 10, e to the 10 is like slightly over 22,000. So this is going to be even bigger than 22,000 times n naught. So if we had no delayed neutrons in our reactor and we asked the question how and we were and that reactor got slightly supercritical, then this example is showing us that in 1 second of time, our neutron population would increase by a factor of 22,000. And that means that our power could also increase by a factor of 22,000 in one little tiny second. So the and that's not going to be good. And so the presence of those delayed neutrons means that we have a bunch of negative exponentials terms in our equation, which end up kind of dampening the overall response of my neutron density, therefore damping the response of my system to reactivity changes when we talk about like how would the power respond or how would the flux respond or any other terms in our any other reactor quantities that we were trying to investigate. So delayed neutrons are really important and they help make our reactors more controllable. Um, so knowing about the point reactor kinetics equations and also the solutions to those, the solution of the n-hour equation, and kind of taking the solutions and the time constants and putting them together gives us a good framework by which we can look at a given system, like look at a reactor and say, is it critical, is it subcritical, or is it supercritical? And also, does it have a source or does it not have a source? And then we can kind of follow the logic that we just talked about to be able to, in lots of different contexts, predict what our reactor is going to do. So we're going to go through some sketches that kind of summarize that. These are all going to be shown for N of t, but you would see the same shape if it was talking about the power or the flux or any other quantity that you could get by multiplying different terms onto the neutron density. So studying these is important. Understanding how to get them is important. It'd be good to like practice explaining them to yourself, maybe practice explaining them to your friends, and kind of working that intuition into your mind in terms of what does a reactor do when these different things happen. And that the starting point is basically just kind of characterizing the system, asking, does it have a source or does it not? And what kind of insertion do I have? Is it a positive insertion, a negative insertion, or a zero insertion? So initially, talking about a critical reactor is probably where we would want to start. And if we have a critical reactor, the blue line is showing the critical reactor with no source. And then the black line is saying, what if we were to add in a source at time t equals 0? So notice if we're critical with no source, then the blue line is just a constant. Oh yeah, and in here we're plotting the normalized neutron density. We're taking the neutron density dividing by its value at time 0. So initially it's equal to 1 because you have n0 divided by n0, which is 1. And then if my system is critical with no source, then we said that my population is just going to remain constant, which means that we just see like a straight line. So if you're critical with no source, then n of t is constant, which is this guy. And if we add in a source, like if at time 0 we add a source into the system, then notice that we kind of increase a little bit quickly at the beginning, but then eventually we increase linearly, which was the argument that we were making before. Um, so this the behavior of the system with a source is a linear increase in that neutron density. So this is just kind of illustrating that. This is our plot showing a linear increase. And it's a good question to ask, which is that when we add a source in the system, does that change our 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 reactivity? Or does that change our multiplication factor? And it's a good question because it's kind of a trick question. The answer is no. And the reason that it doesn't is because when we talk about K and when we talk about rho, those are quantities that are defined in the absence of sources. So we'll say rho and K are source-free terms, are source-free terms. So like when we talk about the multiplication factor of a reactor, it's asking the question, what are the characteristics of my reactor in the absence of any sources? Without any sources, do my productions balance my losses? Um, or how do my production and losses balance or compare in the absence of a source? So when I add in this source to my reactor, it's still critical. Like if we have critical with a source, the reactor is still critical because the addition of a source doesn't affect the criticality of the system, but it does affect how the neutron population responds. And remember that the criticality and the reactivity don't, the neutron population, criticality is not a function of the neutron population. It's a function of the production and loss operators in our system. So we had kind of talked about that before, but that's just a good thing to memorize, or at least to mention again, because it's kind of a it's a weird it's a weird kind of thing. It's kind of a tricky question, but it's important in terms of our terminology and not getting confused. Because if having a source changed the criticality, then you couldn't be critical with a source. So the next one is a supercritical reactor, and we want to basically just start by imagining that we were initially critical. So like over from -5 up to time 0 where something is happening, the reactor is critical, so our population is constant. And then at this point of time t equals 0, a control rod is going to be removed from the core. If we remove a control rod, is that going to add reactivity, remove reactivity, or have no change in our reactivity? Right, perfect. That's going to add reactivity. It's going to lower our absorption, which means that if before our production and our losses were balanced, now we have less absorption than we did before. So now our production is bigger than our losses. And that means that we're going to be supercritical. That means that it's an addition of reactivity. Perfect. And what we see, these two plots are showing how the reactor would respond when the reactor goes from critical to supercritical. And notice both of these increase exponentially. The bottom one is with no source. The blue one is no source, and the black one is with a source. So this is an important thing to mention is that even though we say in both cases, whether it's a source or no source, it's an exponential increase. If you are exponentially increasing with a source, then your population is going to be a little bit higher than the case where you are exponentially increasing with no source present. So that's kind of why the black line is above the blue line, is because you end up increasing a little bit faster if you have a source while you're increasing exponentially. So both are exponential, but if you have no source, it grows a little bit slower than you do if the source is there, which hopefully makes sense. And then this is an example of a subcritical reactor. So this example is saying at time 0, before time 0, we were critical. And then at time 0, a control rod is inserted. So if removing a control rod added reactivity, inserting the control rod is going to remove reactivity. And that is going to take our system into a subcritical state. We're now going to have more absorption than we had before, which is going to mean that our losses are greater than our production, so we go subcritical. And so the blue line is without a source, and the black line is with a source. And so notice that this is on a log scale. So, like initially, they both kind of have a prompt drop, which is kind of meaning that they're both following you. Each of those are going to have a bunch of negative exponential terms that are all going to start decaying away really quickly. And then eventually, like at some time later, the solution for the no source is going to be dominated by that single exponential. And so this looks linear, but it's a linear on a log, it's a linear plot on a log scale. So that means that this is actually showing exponential decrease. which is just like what we would expect. We were subcritical with no source. So our population decreases exponentially. Whereas with the source present, we kind of decrease exponentially at the beginning, but we eventually settle into a steady state. Once all of those negative exponentials have fully decayed away, then all that's left is that particular solution, which is a constant source term. So this is our steady state with a source. Subcritical with a source means that you end up reaching a steady state. So those are kind of, if I were to ask you, those three plots kind of summarize anything that I could ask you about, I have this certain reactor and then something happens to it. It tells you about if there is a source or if there isn't a source and what the reactor does depending on if it's subcritical, supercritical, or critical. So now we can just kind of talk about some things regarding different like kind of conditions that we could talk about. And one of them is the prompt critical condition. Prompt critical means that the reactor is critical only on prompt neutrons. And if there's no delayed neutrons, then that means that if there's no delayed neutron source term, then our point reactor kinetics equations are going to look like this. And this is me rewriting it in terms of the power, um, which we're fine to do. We just multiply through by some constants. That delayed neutron source term is gone, so we could just multiply through by the relevant constants to convert the neutron density into a power. And if we assume that the reactor is critical at the beginning, then what's the rate of change of my power if the reactor is critical? Should be zero, right? And it's exactly zero. And so that means that the left-hand side is zero. And if the power and the mean generation time are non-zero, then if we have zero on the left-hand side, we're free to like divide both sides by the power and also multiply both sides by big lambda. And so what we're going to end up saying is that that reactivity insertion is equal to beta. So that is what that right there is the prompt critical condition. If you are critical only on delayed neutrons, then your reactivity insertion is going to be equal to beta. Um, so if you have an insertion that's larger than beta, then it means that your population can actually be maintained just by prompt neutrons alone. And then this is what my reactor period would end up being. Um, if my reactivity insertion is equal to beta, then I could solve the n-hour equation for omega 0, and then my reactor period would just be 1 over omega 0. And if my reactivity insertion is much bigger than beta, then we can kind of ignore beta in the n-hour equation altogether, because that reactivity insertion term is kind of going to dominate over the beta term right here. And then that means that all of the neutrons that are coming out of my fissions are born prompt, and that means that my reactor period is going to be dominated by big lambda over that reactivity insertion. So this is kind of comparing some various insertions. Notice that each of these insertions is positive. So in each of the cases, we end up increasing exponentially. And and this is showing the relative neutron flux. So this would be phi of t over phi of 0. And so notice at time t equals 0, the value is 1 because we're starting out with a phi 0 over phi 0, which is 1. And then phi of t is going to exponentially increase with time for all of these cases. And these different cases just correspond to different kind of relative to beta. Basically, rho 0 of 0.01 is like where rho is less than beta. Rho of 0.065 is where we're pretty much where we basically have rho equal to beta and we're basically prompt critical. And then the last one is a rho zero of 0.014, which is much greater than beta. And so in all of these cases, you increase exponentially, but notice that the exponential increase occurs a lot faster, depending on how large rho zero is, which kind of makes sense in that if you just have a larger reactivity insertion, you're going to end up with more neutron multiplication. You're going to end up with a larger multiplication factor, and that's going to result in your population exponentially increasing faster than it would if it was like a slightly smaller positive insertion. Um, Technically, reactivity is dimensionless, but it's also one of those quantities that gets these funny units kind of associated with it. So like if usually k is just a number, like k is 1.01, then what my reactivity ends up being is 0.01. So if you answered for the quiz dimensionless, that's perfect. But you could have also answered with any of these funny units for reactivity, and you would technically be right. So this is like the decimal representation of reactivity, but sometimes it's represented in percents or niles or PCM of that decimal value. So a nile is basically 10 to the negative 2. Millinile is 10 to the negative 3, and a PCM is 10 to the negative 5. So it's kind of just like doing basically unit conversions that like if I wanted to take this reactivity insertion as a number and convert it into PCM, then one PCM is equal to 10 to the negative 15. So like if I wanted to take this and convert it into PCM, then I would say I have a rho 0 of 0.01, and I'm going to multiply by 10 to the negative 5 on the bottom, and I'm going to multiply and 1 PCM on the top. So in that case, this right here is kind of like my conversion factor, where I'm currently in decimal units. So I put the 10 to the negative 5 on the bottom, and I put the PCM on the top to convert this into some number of PCMs. So usually like the number of PCMs will be relatively large, but it's just a unit conversion. Similar thing if we talk about reactivity in terms of dollars and cents. That just means if we express our reactivity in terms of beta, then beta is equivalent to $1. And so this is kind of an example of an insertion of 40 of $0.4. So you could be told that an insertion is $0.4 just in terms of our understanding of money, that's equivalent to 40 cents. But also, $1 is equivalent to beta. So $0.4 is the exact same thing as zero point 0.4 times beta. And beta is just a number. Like if it's uranium-235, then we have a value for beta, which is this 0.06854. So if it's zero point 0.4 beta, I could actually plug in that number for beta, and then I would have my reactivity insertion as like a decimal. And then if I wanted to convert this from a decimal value to a PCM value, I basically end up dividing by 10 to the negative 5, which means I end up moving the decimal 5 places to the right. And if I were to take this and move the decimal 5 places to the right, 1, 2, 3, 4, 5, then my decimal ends up right there, and then I have 274.16 PCM. So it's basically these are just unit conversions that you can use to convert back and forth between different kinds of reactivities. If you read like papers about nuclear engineering, and especially if it's like transient analysis papers, you'll either usually see those reactivity values expressed in PCM or in dollars. But it's just unit conversions to go back and forth. It's not really any different from converting like feet to meters or light years or such and such. So like what we were saying about the point reactor kinetics equations and the n-hour equation is that if we have more than two groups, then it's very difficult to solve them analytically. But if we make the one group approximation, then we can actually do analytical calculations with the point kinetics equations, and we can basically fully solve them analytically. So if we only have I equals one delayed neutron precursor group, that's kind of what we're saying. All of our solutions for both the power and the and my precursor concentrations, which in this case, I'm just going to use an overbar for the concentration because I don't need an I now because I'm effectively just lumping all of my precursors into one single group. So the C bar is like the effective concentration of all of my delayed neutron precursors. And these are both going to look like e to the omega t. And if this is what my solution forms are going to look like, then each of these individual, the power and the concentration is going to be a sum of I plus 1 exponentials. So I'm going to have I plus 1 terms, but I is 1. So I'm going to have 2 exponentials because big I is 1. These are the equations that you would use to get effective one group parameters. This would be my effective delayed neutron fraction, which is basically found by just summing up all of the individual beta i's. And this is my effective decay constant, which is found by summing up the abundances of each precursor group divided by the decay constants for each precursor group. So that's what this lambda and this beta bar end up representing. They're just effective one group parameters. And so if there's going to be 2 exponentials for my power and for my precursor density, then our general solutions are going to look like this. I'm going to have an A0 times e to the omega 0 times t plus an A1 times e to the omega 1 times t. 2 exponentials added together with 2 time constants, omega 0 and omega 1. And then my C bar is going to be similar, but the multiplicative constants up front are going to be different. So this is going to look like a B0 times e to the omega 0 t plus a B1 times e to the omega 1 t, where these omega 1s are the same in each solution, and these omega 0s are the same in each solution, but I have different multiplicative constants up front because the A0 and the A1 representing a power are going to be different numbers with different units compared to the B0 and the B1, which are telling me about my precursor concentration. And so these are like standard exponential functions. We could take derivatives of both of these functions. That would be the dp dt, and that would be the dci dt if we were to take the derivatives of these with respect to time. We could then plug those in to this equation, and then we could rewrite the equation in terms of the power and in terms of the precursor density, which would effectively get rid of these time derivatives. So if you were to plug these solutions in and then write this as a matrix form, then you end up with this coefficient matrix times our solution vector of the 2 unknowns that we'd be looking for, which would be the power and the precursor density. And so then the question would be, how do we find the power and how do we find the precursor density? And we already know that to find non-trivial solutions, we want to take the determinant of that coefficient matrix and set it equal to 0. Once you do that, you're going to end up with you're going to end up multiplying these guys together, multiplying those guys together with a negative sign up front. And what you're going to end up with, like when you multiply these 2 terms together, you're going to get some terms that have a factor of omega. You're going to get some terms that have a factor of omega squared, and you're going to have some terms that don't have any omegas attached to them at all. But what you're effectively going to end up with is a polynomial in terms of omega, where A, B, and C are just constants that end up appearing in that equation. And if you have an equation like this, there's only 2 possible roots for omega. There's an omega 0 and an omega 1. And you can solve those by just like using your favorite formula, the quadratic formula, to find the roots of that quadratic equation. And that's going to give you analytical expressions for those roots omega 0 and for omega 1. And then once you know what the omega 0 and the omega 1 are, you can plug them in to your general solution. And so you'll end up getting general, so you can express their general solutions like this, and then you can plug the omega 0 and the omega 1 terms in. And then in the notes, in Dr. Spedkov's notes, he talks about this one group approximation and then assuming some typical PWR values. And by assuming some typical PWR values, what it allows you to do is kind of make approximations about what these constants can be approximated as. It's basically making arguments that like this term is going to be a lot bigger than this term, or this ratio is going to be bigger than this term. And that allows us to kind of simplify the way that we end up expressing those time constants. And so these are the approximate solutions to the point reactor kinetics equations that basically only end up depending on the reactivity insertion and the effective delayed neutron fraction. Also, the effective decay constant and on big lambda. But for different kinds of reactors, in Dr. Spedkov's notes, there's tables of values for some of these parameters. So effectively, these are all numbers that you could either find in the notes or that might be given in the problem. Like they might just tell you what the value of the reactivity insertion is. So when you're doing problem set 5 and you're being asked to plot like the power as a function of time, this is the equation that you could use. Oh yeah, and also I just want to make sure it's kind of the way that this is expressed might be kind of confusing because this is like a matrix. So we're saying the power as a function of time is the initial power times so this thing up front times this guy, and this thing up front times this guy, that's what P of t is. P of t is P naught times this multiplicative constant times this exponential. And this is basically like my A1, or sorry, my A0 and my A1. So I just wanted to make sure that that was clear because that means that this CI is P0 times this guy. That would be like my B0 multiplied by that exponential term. And then this guy right here would be like my B1 multiplied by that guy. So it's kind of, if you were looking at that before, it might have looked confusing because they wrote these things right on top of each other, but that's all that that's kind of show. So yeah, in problem set 5, you have a question where it's like asking you have a reactor that starts at some power, and then you have a series of reactivity insertions that you use to get a plot of how that power changes with time. And so these are the equations that you could use to get to do those problems. And yeah, so that's kind of the stuff that I wanted to say about transients. And when we talk about transients, up till this point, we've ignored something that's really important, which is a phenomena called feedback. Um, in general, feedback is gonna happen because when you have a change in like the neutron flux, that's gonna change other reactor properties. And those properties can affect how my neutron population behaves. So like, for example, um, if I have a reactivity insertion that increases my neutron density, that increase in my neutron density is going to increase my neutron flux. And if I have an increase in my neutron flux, that can increase my reactor power. And if I increase my reactor power, that's going to end up like heating things up more. So, and that's going to affect the temperature of my reactor and of the materials in my reactor. And it ends up being temperature changes that end up dictating a lot of the feedback in my reactor. So a lot of feedback in the reactor is going to be caused by temperature changes. And when I have temperature changes in my reactor material, that is going to influence properties in my reactor. And the temperature is going to be influenced by the temperature is going to change because of changes in my heat generation rate. So that temperature is going to be influenced by changes in my heat generation rate. And the heat generation rate is the same thing as my fission power, which is PF in the notation that we've been using so far. And my fission power is going to be determined by the fission rate. And the fission rate is going to be determined by the neutron flux, by my neutron population, which also depends on the neutron flux. So we can say population and the neutron flux. And so why does changing temperature end up affecting other things in my reactor? Well, remember that our cross sections are a function of energy, and that certain things happen with our cross sections when temperature changes, like Doppler broadening of our cross sections can increase resonance absorption. So our cross sections also end up depending on temperature. And when we talk about reactivity, that's about my production rates and my loss rates. And my production rates is going to be dictated by a fission cross section, and my loss rates are going to be dictated by like an absorption cross section. So by changing cross sections, I end up affecting my reaction rates, and those reaction rates end up affecting the multiplication of my system and the reactivity of the system. So those end up affecting the reactivity and the multiplication factor because those end up depending on cross sections. So there's a lot of complicated kind of like interdependencies of these quantities on each other. You make one change in the system, and that change has a lot of other impacts that can affect all kinds of other things in my system. So the next thing that we want to do is just kind of like give a simple illustration of a possible feedback process. So, like, we got a reactor that's critical, but it's critical at a very low power level. So that means that the fission production is like so small that we're not really like heating things up very much, that the reactor core is like at a similar temperature to the surroundings. And then we want to think about the fact that if that reactor has control rods, we could remove those control rods from the system, which would add positive reactivity into the system. And so we so now we went from critical to supercritical. And if we're supercritical, that means our neutron population is going to increase exponentially. That means that the flux is going to increase exponentially. That means that the reactor power and the fission rate are going to increase exponentially with time. And if my fission rate and my power are increasing exponentially with time, that means that my fuel is going to start to heat up. Heating up of my system is going to change the temperature. That's going to end up changing my cross sections. And the way that the cross sections are affected by temperature is that as temperature goes up, resonance absorption increases. And the increase in resonance absorption means that instead of neutrons being able to cause new fissions, they get parasitically captured in certain materials. And that means that instead of the chain reaction, like kind of running away and continuing to exponentially increase forever, the increase in temperature and the increase in the increase in my absorption ends up actually dropping the multiplication of my system. So that is actually a really good thing because it means that our reactors are controllable not just from delayed neutrons, but also because of like inherent feedback mechanisms that result in temperature not being able to just like increase indefinitely. So And basically what would continue to happen is that as that temperature grew and grew and grew, that multiplication factor, the cross sections would respond, you would get increased absorption, and eventually you get so much absorption that you kind of start to see that multiplication factor dip. And eventually that multiplication factor would actually settle back down to 1, and your reactor would settle into like a new steady state at some time after the initial reactivity insertion happened. So this is an example of negative feedback. And negative feedback is good because it gives our reactor stability. If you try to design a nuclear reactor and you want to get your reactor licensed, one of the things that you have to be able to demonstrate is that your reactor has negative feedback mechanisms. Because otherwise, you could have a situation where all of these same things happen. You're critical, you remove a control rod, that causes an increase in your neutron population and an increase in your power. And if you don't have negative feedback, then that's just going to exponentially increase forever, and then your reactor melted down, and then a lot of people are really sad. Um, so demonstrating negative feedback is really important, and it helps make our reactor stable and more controllable. So yeah, nuclear reactors are complex systems. They have a lot of interdependencies, and the system is like all of these things that are connected together, and you have inputs into that system, and then the system responds, and then there's certain outputs to that system. Like an input to our system might be a reactivity insertion, and then the output might be like how the power responds to that insertion. And with feedback, you have a feedback loop where the outputs end up influencing the input. So like this is illustrating what I was just talking about, where I have a reactivity insertion. That insertion affects the power. It causes the power to change, and it causes the power to go up. That change causes my temperature to increase and to go up. But that increase in temperature ends up affecting my cross sections such that the fission rate goes down and the absorption rate goes up. And when the fission cross section goes down and the absorption cross section goes up, that actually slightly adds negative reactivity to my system, so that whatever that initial positive reactivity was gets slightly decreased, and now I have a lesser reactivity insertion in my system. And so that's a process of a feedback loop by which changes in my system end up affecting that initial quantity that was affecting the system in the first place. So that's the feedback loop illustration of the scenario on the previous slide. And in general, if you have positive feedback, then the system gets amplified by that initial change, and that makes your system unstable. Um, and with negative feedback, you have dampers that end up reducing that initial change, which makes your system more stable. Um, it's kind of like when you're driving in your car has shock absorbers, which dampen bumps. So like if you didn't have, that's an example of negative feedback because it's like you drive and you hit a bump and you kind of bump a little bit, but then you like kind of settle out after that. So that's like a dampening or like a negative feedback response. The opposite of positive feedback would be you hit that bump and then it makes you bump more and more and more and more, and that would be very unstable. So we always want to design reactors that have negative feedback because it makes our system stable and more easy to control. So that is where I think I will stop for today. Um, and when we come back tomorrow, we're gonna talk about the last topic of chapter 7, which will be the last thing that you see on exam 2. And that's going to end up talking a little bit more about different feedback mechanisms and also a little bit about something called perturbation theory. So that was all that I had for y'all. If y'all have any questions for me, feel free to let me know. And if not, I hope y'all have a good rest of your day and a good weekend. And I'll see y'all on Monday. Oh, before y'all go, I have some quizzes to pass back if you were here for quiz 6.